Previously, we discussed convergence of series. Well, here I will discuss absolute convergence. Absolute convergence is a stronger property for series, and it boils down to this definition. A series of partial sums of a sequence an is absolutely convergent if the sum of the absolute values of an is convergent, right? So let's discuss this property by means of two examples. The first example that I'd like to discuss is the alternating series where I have as underlying sequence 1 minus 1 to the power n divided by 2 to the power n. This is a series that is not only convergent, but it's also absolutely convergent. That it converges can be concluded right away from the alternating series theorem, since 1 over 2 to the power n is a monotonically decreasing sequence with limit 0, but it's also absolutely convergent. Well, why is that? Well, if we look at these terms and we put absolute values around them, then we get as an absolute value 1 over 2 to the power n, which is a geometric series with which is converging and has a sum 1, as we've seen before. Okay, so if we now look at the series minus 1 to the power n divided by n, then again the underlying sequence is an equals 1 over n. It's an alternating series with underlying sequence 1 over n, which is monotonically decreasing and has a limit 0. So this series has a sum, right? So it is convergent, but if we now take the absolute values of these terms, minus 1 to the power n divided by n, then we get 1 over n as a result, and the series, the corresponding series, is the harmonic one, which has an infinite sum. So it does not converge in absolute sense. Okay, now I will discuss the following property, that absolute convergence is stronger than convergence as a property. So if you know that a series is absolutely convergent, it is automatically convergent. Well, a proof is not at all that hard if you know what to do, so I will include a proof right away. So consider a sequence an, and suppose the series, the corresponding series, is absolutely convergent. So this means that if we look at the sum from n is 1 to infinity of the absolute values of an, then this sum exists, right? So we have a limit of the partial sums, and suppose we call this limit s. Then we also have, trivially, if we double all the elements by taking 2 times the absolute value an, then of course the sum doubles, right? So we also have that the series with underlying sequence 2 times the absolute value of an equals 2s. Okay, now we're gonna define a different sequence, and this sequence we will call Bn. And what is Bn? We're just gonna add up the value of an and the absolute value of an. We do it for all n, all natural numbers. Yeah, what we immediately can see is that these are all non-negative terms, right? So Bn is always larger or equal than 0, right? And also we have if we take instead of an the absolute value of an over here, then we increase the value that is listed here. So we also have that Bn is smaller equal than 2 times the absolute value of an. Okay, so now have a look at the partial sums over Bn, right? So look at the partial sum over Bn. So the partial sums from k equals 1 to n over bk. What can we conclude over these partial sums? Well, first of all, we keep adding elements that are non-negative. So if we look at the sequence of partial sums, then we see that this is an increasing sequence, right? Moreover, yeah, so the partial sums are monotonically increasing. Moreover, we also have the following property, that bk is smaller than 2 times the absolute value of ak, right? So in particular, if we sum up and the sum of k equals 1 to n bk is smaller equal than 2 times the sum over all these absolute values of an, and this sum was equal to 2s. Okay, so now let's proceed. That now we have the monotonic convergence theorem if we apply it to the sequence of partial sums over Bn, right? So the partial sums are monotonically increasing and bounded by 2s. So the monotonic convergence theorem says that the partial sums related to this sequence bk should converge, right? And what does it mean? It means that the sum of n k equals 1 to infinity bk, this sum exists, right? Okay, but now we do the trick. Now you will recognize why we took this special sequence bk, since now the sum of k equals 1 ak is equal to the sum over bk's, and the bk's, they add something additionally, right? So they add the absolute value of ak. So to keep equality here, we should subtract a sum of all the absolute values from k's of ak from k's 1 to n, right? Okay, but now take limits on the left side and on the right side. On the right hand side, we have seen that this limit for n to infinity exists, right? And we also, by absolutely convergence of this of the series an, we know that this also has a limit, and this has a limit 2s, and this also has a limit. So if we take limits, then we on the left hand side, on the right hand side, we get a sum s star by summing over all bk's, and we get minus 2 times s, or minus s. So what we have now is that the sum from k is 1 to infinity over ak equals s star minus s. So what we in particular see is that the sum over AKs is convergent. Yeah, so we get convergence, and that's what we'd like to show. So if a sequence or a series is absolutely convergent, then it's also convergent.